Okay, so where we left off last time was talking about how APIs get used to interface between applications and different network technologies and makes life a lot simpler. So, typical case of that, you have what's called a network stack. So, within a particular device, you have a series of functions that any communication goes through. So, for example, if you're trying to send out an email, that email is running through some application on your machine. At the end, for that email to get released into the network, it has to go through your physical media, right? Basically like your network card. So, and in between that, there's a bunch of different processes that can happen, like encrypting the email if you need to, like looking up the destination address of wherever you're sending it, controlling when the device actually does the transmission. All that kind of stuff happens in these intermediate layers. So, layers are designed as modules. So just like APIs that we've talked about, we don't have a specific way that the module is going to work. What we do is define what its inputs are, its input format, and its output format. And as long as the module can meet those limitations, then everything's fine. Okay, so we can make a change to one module. As long as we don't change the input format and the output format, nothing in the rest of the system has to change. Okay. So, encapsulation, basically each one of these layers acts as its own, self-contained unit. So the layers only rely on the ones below them. So essentially, well, if we're saying the data comes up, if I'm receiving an email, I know that if I'm receiving something from physical media, it's going to be in whatever standard form that the packets come in. Right, so it would be some kind of bit stream initially, some sequence of ones and zeros. That's what this physical media is going to get. So this layer 1 is going to need to process that stream of ones and zeros and turn it into something useful that the next layer up can handle. Okay. Because of this structure, this system is very, very flexible. We can reuse code in various places across the network. So if I find one technique that works well for processing within a layer, I can use that anywhere else, right? As long as, again, the inputs and outputs are the same, doesn't matter what I can use, so it's very easy to reuse these structures. Also, I can change the module implementation. So, for example, if I come up with some sort of new encryption technology that maybe happens at layer N up there, I can change that. I can implement that new technology in the module without affecting the rest of the stack. Okay. So, remember we've talked about loosely coupled versus tightly coupled systems. This is an example of a loosely coupled system, right? So, the parts of the system components, they only interact through these standard interfaces, which makes it very easy to modify. I can change this layer, whatever, without affecting the rest of the system. Now, it is true that if I came up with some way to share information across layers, I might be able to make the system work a little bit better. If I had a more tightly coupled system, tightly coupled systems generally offer higher performance. But the downside is they're difficult to modify. So sometimes you'll have people design various what are called cross-layer schemes, where data from one layer gets shared across with other layers. And yeah, you can always devise some kind of cross-layer system that's going to perform better in terms of pushing data through faster or yeah, I mean, I guess that's what it would be, is pushing data through faster. But its modification is going to be very, very difficult. Because then again, if it's if it's a cross-layer system like that, you change something in one layer, you got to worry that it's going to have impacts on everything else. Okay? All this makes sense? Questions? Okay. So, let's talk about sending out data as if we were doing package shipping, which everyone should understand. Okay, so I'm up there in the upper left. I have a friend on the other side of the world, let's say in Australia, and I want to get a package ready to ship. So I'm going to send him, I'll send him a pineapple. So I put a pineapple in the box. What do I have to do to send the pineapple in the box through the mail? Who has ever mailed a package? What do you do? I got a box, I got a pineapple. What do I do? Print a label. I'll accept that. What else? Okay, what else? Do I ship what's the shipping? I say, I have a box with an address on it, and here you go, ship it. What are they going to say? Why are they going to tell me where to stuff it? What important step have I not done? No, pineapple's in the box. We'll assume that. We'll assume the pineapple's in the box. There's an address label. I haven't paid him. I haven't bought postage, right? Yeah. So you put some stamps on it. Now I know you can take it to the thing and show it to them, and they'll say, here's how much it costs. But we're going to assume I have the package actually ready to ship, which means the stamps on it. Okay? So I give it to them. They put the package. They say, okay, thank you. It's paid for. They load it up on a plane or a boat or something. It's going to Australia. Okay? What's the path from Chicago to Australia? Let's say the first place it goes is LA. Okay? So somewhere in LA, package comes off the plane. Somebody's going to look at it and say, okay, it's at the right place. It's in LA, but it's not the final destination, right? The label says for Australia. So they ship it onward. Let's say the next step is Honolulu, right? It goes through Hawaii. Same thing happens. They take the package off the plane. They look at it, okay, this is supposed to be in Honolulu right now, but Honolulu is not the final destination. So they ship it on to the next one. Say it goes to Sydney, right? Say my friend lives in Sydney, so they can, drop off the package and they load it up onto a mail truck, and eventually he gets it. Okay? We understand this. This is easy, right? Basically the same thing that happens with packets getting shipped around through the network. Okay. So the first one I'm going to introduce is the 7-layer OSI model. Okay? Now, key thing about OSI, it was never actually implemented anywhere. So in the early days of the internet, there were two competing models for basically how network traffic would be handled. One model was OSI, which fairly rigidly wanted to specify how everything happens. The people who were behind OSI had a whole lot of ideas about how they wanted every little thing to work. On the other hand, TCP/IP, which is the one we'll talk about in a minute, which is the one that actually uses, is a lot more flexible. It allows a lot more leeway in how the delivery process happens. Because of that, what happened historically, the OSI guys, they couldn't all agree on one standard way to do things, right? Because your telecom people wanted it one way, the computer science people wanted it another way, and even within those, they had a lot of competing interests. So while those guys, the OSI guys, were all tangled up in endless meetings that they were never going to come to an agreement to anyway, the TCP/IP people said, have fun, we're going to go start the internet, which is basically what happened. So basically it works in terms of layers. So I'm going to lift this. If we look at how a message is going to get sent over a network, essentially, okay, so here's the source. I'm going to say the source is me. Why it's so laggy there? There we go. The source is me. I'm sending out something, right? So I have an application. Let's say I'm sending out an email. We'll put in some other content in a minute. So I send it to the application. What do I have next? I send it to what's called the presentation layer. Presentation layer, well, I'm just going to write these in and then we'll talk about them in a minute. Move this up just a tiny bit. Move that to 16. That'll work. Okay. And a lot of this I can borrow over here. Okay. And over here we have the destination. Okay. So what'll happen, I send a packet, I send a communication out, like I send an email out, it goes through all these layers until it reaches the physical layer. The physical layer is like, the network card that sends it out into the network. Okay? It goes over the network somehow until it ultimately reaches my friend's computer. Okay? Whoever I'm sending the email to might be not a friend, might be an enemy. Okay? And then once it reaches there, it goes up to their email application. Okay? We can understand this. This makes sense. We haven't talked about the layers yet. That's okay. But we understand the model. I send out an email. It goes out into the network. The other computer receives it. Goes through those same layers backwards. Okay, this is the OSI model. So key things that happen. Number one, okay, the application, right, where the data comes from. Okay, so I have an email application. I send out that. Presentation layer controls, basically makes the data ready to send over the network. So things like encryption or compression, those would typically happen in the presentation layer. Okay, so if I'm sending out an email and I need it to be encrypted and safe, right? As soon as the data leaves the application layer, I send a stream of, I click send, I send some raw data to the presentation layer. Presentation layer will produce some data stream that's ready to be sent. In this case, would be encrypted. Session layer, it does a couple things. Number one, maintains session connections. So if I'm logged into an email application, it remembers that I still am. Also, synchronizes related traffic streams. Say related data streams. So on YouTube, for example, you have two streams typically. You have an audio stream and a video stream, and they need to be synchronized so that they all play together. So the session layer is responsible. It's going to take those two, that combined stream of data, split it into two at that point. Okay. Transport stream, what it does, chops message into packets. So we talked before, packets are basically the envelopes for data, about 1.5K. So if we have a big attachment to our email, we need to chop it into a whole bunch of packets. Okay. Network layer finds the destination IP address and attaches it to each packet, right? Basically, that's putting the address on the envelope. Looks up where it's supposed to go to. It has to consult some outside data source to do it. Once it gets that, it attaches that information to each packet. Okay. The data link layer controls the schedules transmissions. That's one thing. Schedules transmissions. Basically figuring out when your device has a turn to actually transmit each packet, and converts packet data into what's called a bit stream. So a bit stream is a sequence of ones and zeros that the physical layer is ultimately going to send out, right? So the data link layer gets a packet with all this network information attached onto, but it needs to convert it into a bit stream so the physical layer can send it out. And the physical layer actually sends out the data. Okay? On the other side, those same things happen in reverse, right? The physical layer receives the data link layer checks and says, is this packet for me, right? Am I the next step? If so, it keeps it. If not, it passes it onward. So I'm going to add this. So incoming packet, am I the next step on the path? Okay, so just like we had in our airplane shipping example, every place it went to, LA, Honolulu, they looked at the package and say, good, the package is where it's supposed to be right now. It's in LA, but we're not the final destination, so we ship it onward. The data link layer does that. Network layer says, am I the final destination? Okay? If so, then it goes up through all these other layers, right? So you have a stream of packets that the transport layer joins together into a message. Session layer synchronizes them. Presentation layer does decryption, decompression. And the application layer says, hey, you got some email. So if yes, right, then you go up there. And if not, you send it back down to the physical layer, right, to the data link layer to get resent. Okay, does this make sense? This is essentially the OSI model. Now, what do you need to know? Well, we'll talk about that in a minute, right? At the end, I'll have a little recap of key things you need to know. But these are the 7 layers that it goes through. Now, anytime you have some kind of network communication, it's basically going to need to go through these kind of steps. But TCP/IP, I'm going to say we make it a little simpler. Number one, we group some of them together. They're grouped a little differently. And last, the physical layer is not even specified. So, OSI wants to specify everything. TCP/IP is a lot more flexible. Let's talk a little more. Yeah.
Can you explain the session again?
Well, one thing that the session layer does is that's where the information, suppose you're connected to a website, like you're connected into Google Mail, to Gmail, and you know that it's a persistent connection, right? You can like close it out and you come back and that stuff is still there, it still knows you're there. Yeah. Session layer is responsible for that, right? And for example, if you click on an email and it opens it up, and could be a new URL. If you click to open an email in a new tab, it remembers it's you. Session layer does all that kind of stuff. Exactly. Right. But strictly speaking, that's not part of this whole traffic flow. It's just something I mentioned. Yeah, the session layer keeps that information, and that's why it's called the session layer. Okay. But the relevant thing that it does is if you have related data streams, like on YouTube, it synchronizes them so that they all go out at the same time. Okay. So that's that information there. Another thing, switching versus routing. Okay, so we've talked a little bit, but here I'm throwing it all on a slide. So switching and routing, two different techniques for packet handling. Basically, for switching involves direct connection between devices, typically within a local area network. So you have, for example, at home, you have a router hooked up to the wall, probably with a wireless access point attached to it. Devices can directly connect to the router, right? You plug in an Ethernet cable, that's a switch connection. Or they can connect to the wireless access point, which is basically equivalent. But it's not, a physical connection. If you had a big local area network, you could have a big switch box with a whole bunch of ports that, a few dozen devices connect directly to each other. Okay. So that kind of network traffic through switching gets processed at the data link layer, right? So remember back in our image here, when a packet comes in, right, the device is going to look and say, am I the next device on the path? Because you could have a whole sequence of devices that you could go to, and one device could be connected directly to a bunch of other devices, and it might send out the packet to all of them, but the packet itself might only be for one of those. So every device is going to look at it and say, is this packet that I'm receiving, am I the next person who's supposed to handle it? Okay? That happens at the local level, local area network level, with a switch connection. Routed connections, though, routing is connection between devices in different networks. So, for example, if you want to send an email from your network to another network, right, you go through a routed connection. So your router sends a message to another router, probably with a bunch of other routers in between. That traffic gets processed at the network layer. So anytime this packet comes in, right, a particular device receives it, looks at it, says, okay, I'm the next stop on its path, and it looks at it and says, am I the final destination? Does the destination IP address on it actually match what's on the packet? If so, then it processes it upward. If not, it kicks it back down. Okay, but for routed traffic, the network layer gets involved. Okay, so the core problem for routing, if there's an incoming packet, number one is the destination in my network. For example, you send the packet all the way around the world, it gets to that other router. The router knows all of the devices that are in the local area network. The router can say, oh, yeah, this device is in my network, I'll forward it on. And also, if the data link layer finds the packet is for me, it can ask, am I the final destination? Okay, so switching, direct connections within a network, routing, indirect connections in other networks. Routing is the process of sending data across networks. Okay, so TCP/IP, now we've gotten to it. So every computer and network on the internet basically uses the same protocols, right? Reason is so they can communicate with each other. Everything we've talked about with APIs is designed about bringing about a standard communication model. Well, regardless of what that model would be, everybody pretty much needs to use the same one. So TCP/IP is the one that gets used these days. So it covers most of the same functions and sequence as the OSI model, but it's very flexible and doesn't demand strict adherence. So there's a couple things I will cover. So number one, in TCP/IP, so I'm going to mark this in blue, these layers are combined. What does that mean? Well, in the OSI model, you would have to strictly go through that sequence. The application layer would feed data to the presentation layer would feed data to the session layer feeds data to the transport layer. In TSI, it doesn't have to happen that way. For example, you might combine the data streams in the session layer, and only after that do you compress them, right? So you could have that option to not send them out separately. Other stuff you could do encryption afterward. It's not a strict sequence. So anything that happens in here, the output of this cluster of layers gets sent to the transport layer. So it allows more flexibility in how applications are set up. The transport layer in TCP/IP is basically the same. Network layer is basically the same. So here's called application layer. It's called the application layer in TCP/IP here. This one is called the transport layer. This one is called the internet layer because the network is the internet. And this one is called the link layer. Okay, so same functions essentially, but different names. The last one though, physical layer, not specified in TCP/IP. Okay, not at all. Reason is, as long as the data link layer produces standard output, I don't really care what the physical device is as long as it can accept that standard output. Okay, so this is one of the big problems with TCP/IP is that the network people, the telecom people, they wanted to rigidly specify how the physical layer worked. But they're trying to do this in the 70s, right? And anybody with any sense would know we have no idea what's coming down the pipeline over the next 20, 30, 40 years, right? No idea. I mean, we know stuff is going to get better, but we don't know what the devices are going to look like, how they're going to work, all that. So the data link layer, it just says data's coming out in this standard bit stream. Can your physical layer accept a standard bit stream? If so, great. Problem solved. You can use your device. Okay? That's one of the key flexibility aspects of TCP/IP. Okay. Anyway, so if your device uses TCP/IP, it can exchange data with any other type of computer that also does. That's the wonderful thing about having this standard model. Okay. Questions on this? So this is the basic stack. Yeah. Yes. I mean, for purposes of the exam, right, TCP/IP has 4 layers. OSI has 7. Where the TCP/IP layers are these 4. They're grouped together like that. Doesn't have the physical. Okay, and I explained to you why it doesn't have the physical. Because you're like, doesn't it still need to send out data? Well, of course it does. It just doesn't specify how the physical layer needs to work. Okay? All right. So the protocol layers, again, for TCP/IP, the application layer, transport layer, internet, link, and I showed you a minute ago how they're all combined. So, okay. So the basic stuff here, basic process for TCP/IP, suppose you're sending out an email, the application layer, you press, you write your email, you do any attachments, you press send. That sends all of your data to the transport layer. Transport layer is going to take that information and chop it into packets, right? Maybe they're encrypted when they get to the transport layer, maybe not, but transport layer is going to take whatever data it gets and chop it into packets. The network layer, that's going to assign IP addresses to each packet, so where it's going to go. The link layer, right, is going to handle this next step transmission. So yeah, it's going to go down through the physical layer, but they didn't draw it here. But basically, at the link layer, through direct connections, there's going to be a series of devices that the email is going to go through. Each time, the device receives it at the link layer, says, okay, thank you, I got the packet. Then it looks up and says, oh, but I'm not the final destination, so I got to forward it with a new transmission. Same thing, eventually it gets to the final destination, receives the packet, passes it up to the network layer looks at it and says, okay, this is for me. Then sends those packets to the transport layer accumulates a bunch of packets, eventually is able to assemble them all into the message, and the little flag goes up in your email box, says you have a message. Okay? Easy, right? What? Good enough, okay. So, TCP/IP versus OSI. So again, TCP/IP has only 4 layers, OSI has 7. TCP application layer encompasses those 3 from OSI, application, presentation, and session. The other ones are roughly equivalent, slightly different names. So, unlike OSI, TCP/IP does not specify a physical layer, but only the format of inputs and outputs from the data link layer, for the link layer. So, As long as the formats there are correct, any physical device will be perfectly fine. Interesting article. If you want to look at this, all this kind of stuff I've been talking about, little article here, so some tech history, OSI, the internet that wasn't, right? Basically why it failed. Okay. So, let's do a recap. Stuff you need to know. All right, because there's a lot of stuff in this section, but not all of it is stuff that I expect people to know. Let's see, I got to do something here. See if we can get, there we go. So, number one, what's the internet backbone? You should know what that is. What are tier 1, 2, and 3 ISPs? What are peering and transit agreements? Okay, simple stuff. What's an API? Why are they important to the internet? Why are APIs important to the internet? Okay, that's good enough. Yeah, right? Basically, if you have a standard API, you control the kind of the format of the content that gets sent out, and then a bunch of different devices, technologies, applications, whatever, they can all use that same API. So you always need an interface between different types of things, right? So Microsoft Word application produces a different data format than packets. You need some kind of translation there. Okay, but the fact that you use standard APIs and then you reuse them, everybody on the internet agrees to accept this standard packet format. That makes life a lot simpler. You don't have to design a custom translation process for every pair of applications and technologies. Okay. Number two, what is routing? We talk about typical problems in routing. We may have skipped that. Yeah, okay. Well, I mean, it's implied. I think I drew a picture with switches back when. So, what is routing? Routing is sending data across networks, right? In contrast to switching, switching is sending data within networks. How are typical problems addressed? Well, the internet is tremendously redundant. Okay, so in general, if one piece breaks down, there's another path that can be used to bypass it. That was the picture I drew the other day. Excuse me. Layered protocol. So then we had two, right? OSI, TCP, IP. So number one, what's a layer? A layer is basically a modular software component that handles a process in a particular standard way. A layer accepts a standard input, produces a standard output. Okay? So for example, the transport layer accepts some slug of data from an application and produces a sequence of packets. All right. How are these layers defined? Well, they're defined in terms of roles, right? The specific things you want each layer to do. And why are they separated? Well, they're separated so that you can make changes to one layer without having to reset everything else in your network stack. Okay? That's the key thing. So example, imagine if anytime you changed your physical media, all of these other layers were dependent on it, and basically you have a new physical media, you have to reinstall all your applications with a new version, right? Colossal pain in the ass. You don't want to have to do that. Okay. So, OSI 7-layer model, should know the 7 layers. Okay, you should know that it exists. So, if you want to remember this stuff, right, mnemonics are your friends. So you have A, P, S, T, N, D, P, which of course stands for all people seem to need delicious pizza. Because we all need delicious pizza. All right. So, TCP/IP, what are the layers? There's 4 of them. What do they do? You know, how do they correspond to the OSI ones? And then the big picture, how are OSI and TCP/IP different? OSI is more rigid, TCP/IP is more flexible. OSI has 7 layers, TCP/IP has 4. What's the grouping? You know, the application layer in TCP/IP corresponds to 3 layers in OSI, and TCP/IP does not specify a physical layer. Okay? That's what you need to know from this chapter. All right.